Forcing frequencies in gearbox analysis, understanding dynamic forces affecting gearbox performance. Forcing frequencies in gearbox analysis, overview of gearbox forcing frequencies, shaft rotational speed and frequency, single-stage gearbox speed relationship, gear mesh frequency, GMF, calculation, sideband frequencies and modulation, two-stage gearbox configuration, two-stage gear mesh frequency calculation, sidebands in two-stage gearboxes, engineering applications and diagnostics. Forcing frequencies are the fundamental excitation components generated by rotating and meshing elements within a gearbox and are central to vibration-based condition monitoring. In gearbox analysis, these frequencies originate primarily from shaft rotation, gear tooth meshing, and the modulation effects that produce sidebands. Understanding how these frequencies are calculated and how they relate to gearbox geometry and operating speed allows engineers to interpret vibration spectra with confidence and accuracy. In a healthy gearbox, forcing frequencies appear as predictable, repeatable spectral components at known locations. Deviations in amplitude, the appearance of harmonics, or the growth of modulation sidebands often indicate developing faults such as gear tooth wear. Cracking, eccentricity, or misalignment. This presentation focuses on engineering methods to compute forcing frequencies for both single-stage and two-stage gearboxes. It begins with shaft rotational frequencies derived directly from operating speed, progresses to gear mesh frequencies driven by tooth engagement, and then explains how sideband frequencies arise from amplitude and frequency modulation. Emphasis is placed on practical calculation steps, physical interpretation, and how these frequencies are used in real-world gearbox diagnostics. By grounding the discussion in classical vibration theory and standard gearbox kinematics, the methodology presented here can be applied consistently across industrial gearboxes used in power generation, oil and gas, manufacturing, and marine applications. The approach taken is analytical rather than purely empirical. Each forcing frequency is tied directly to measurable gearbox parameters such as rotational speed and gear tooth count. This ensures traceability between vibration data and mechanical design, which is a key requirement for professional engineering analysis and reliable fault diagnosis. The image illustrates a typical gearbox configuration used to explain how rotational motion and gear meshing generate predictable forcing frequencies that appear in vibration spectra. Gearbox forcing frequencies can be grouped into three primary categories: shaft rotational frequencies, gear mesh frequencies, GMF, and sideband frequencies. Shaft rotational frequencies correspond to the fundamental speed of each rotating shaft and typically appear at low frequencies in the vibration spectrum. These components provide the speed reference for all higher frequency phenomena and are critical for validating correct speed inputs during analysis. Gear mesh frequencies are generated by the periodic engagement of gear teeth as torque is transmitted from one gear to another. Each time a tooth pair comes into contact, a force pulse is generated. The repetition rate of these force pulses defines the GMF, which is usually one of the highest energy components in a gearbox vibration spectrum. Harmonics of GMF often appear due to nonlinear stiffness, backlash, or tooth profile deviations. Sideband frequencies occur when the gear mesh vibration is modulated by lower frequency phenomena such as shaft rotation, load variation, or manufacturing errors. This modulation produces spectral lines symmetrically spaced around the GMF at integer multiples of shaft speed. The presence, spacing, and relative amplitude of sidebands are powerful diagnostic indicators. Together, these three categories form the foundation of gearbox vibration analysis and enable engineers to separate normal operating behavior from fault-related responses. This image shows a rotating shaft and associated components, highlighting the physical origin of shaft rotational frequencies used in vibration analysis. Shaft rotational frequency is the most fundamental forcing frequency in any gearbox system. It is derived directly from the shaft speed, which is typically specified in revolutions per minute, RPM. For vibration analysis, shaft speed must be converted into frequency units of Hz Hc using the relationship F equals RPM/60. This conversion establishes the base frequency used to identify harmonics, modulation effects, and speed-related faults. In a gearbox, each shaft may rotate at a different speed depending on the gear ratio. The input shaft speed is usually known from the driving machine, such as an electric motor or turbine. Output shaft speed is calculated by dividing or multiplying the input speed by the gear ratio, which is determined by the number of teeth on the mating gears. Accurate identification of shaft rotational frequencies is essential because these frequencies often modulate higher frequency components, particularly the gear mesh frequency. From a diagnostic perspective, excessive vibration at shaft speed or its harmonics can indicate imbalance, misalignment, bent shafts, or looseness. Therefore, correct calculation and confirmation of shaft rotational frequencies form the first step in any professional gearbox vibration analysis. In a single-stage gearbox, power is transmitted through one pair of meshing gears, making the speed relationship straightforward to calculate. The speed ratio between the input and output shafts is defined by the ratio of the number of teeth on the driven gear to the number of teeth on the driving gear. Mathematically, the output shaft frequency is equal to the input shaft frequency multiplied by the ratio of driver teeth to driven teeth. This simple relationship allows engineers to determine all shaft speeds in the gearbox once the input speed and gear tooth counts are known. Because vibration forcing frequencies scale directly with shaft speed, accurate speed calculation ensures correct placement of spectral markers during analysis. In practice, discrepancies between calculated and measured shaft frequencies may indicate slippage, incorrect gear data, or instrumentation errors. Understanding the speed relationship in a single-stage gearbox also provides the foundation for more complex multi-stage systems. It reinforces the principle that all higher-order forcing frequencies, including gear mesh and sidebands, ultimately depend on accurate shaft speed determination. The image depicts gear tooth engagement, visually linking the physical meshing action to the generation of gear mesh frequency. The gear mesh frequency is generated by the repeated engagement of gear teeth during torque transmission. It is calculated by multiplying the shaft rotational frequency by the number of teeth on the gear. For example, if a shaft rotates at 10 Hz and the gear mounted on that shaft has 40 teeth, the resulting GMF is 400 Hz. This frequency represents the rate at which tooth contact forces are applied. GMF is typically the dominant frequency component in gearbox vibration spectra due to the stiffness variation and impact forces associated with tooth meshing. Harmonics of GMF often appear and can extend to very high frequencies, particularly in high-speed gearboxes. In a healthy gearbox, GMF and its harmonics are stable and well-defined. Changes in GMF amplitude, the appearance of sidebands, or broadband energy around GMF are strong indicators of gear-related faults such as tooth wear, pitting, cracking, or lubrication problems. As a result, precise GMF calculation is critical for reliable gearbox diagnostics. Sideband frequencies arise when the gear mesh vibration is modulated by a lower frequency source, most commonly shaft rotational frequency. This modulation can be caused by load variation, gear eccentricity, misalignment, or localized tooth defects. Mathematically, sidebands appear at frequencies equal to GMF plus or minus integer multiples of the modulating frequency, typically the shaft speed. In vibration spectra, sidebands appear as evenly spaced peaks around the GMF. The spacing between sidebands corresponds directly to the modulating frequency, making them highly diagnostic. For example, sidebands spaced at input shaft frequency around GMF often indicate input gear defects or eccentricity. The relative amplitude and symmetry of sidebands provide insight into fault severity and location. Light, symmetric sidebands may indicate early-stage defects, while strong, asymmetric sidebands often signal advanced damage. Proper identification and interpretation of sidebands require accurate calculation of both GMF and shaft frequencies. This image shows a multi-stage gearbox layout, illustrating how power flows through successive gear meshes. A two-stage gearbox contains two successive gear pairs, resulting in multiple shafts, multiple gear mesh frequencies, and more complex forcing frequency relationships. The output of the first stage becomes the input to the second stage, and each stage has its own gear ratio, shaft speeds, and GMF. To analyze a two-stage gearbox, engineers must calculate shaft speed sequentially, starting from the input shaft and applying each gear ratio in turn. Each shaft then serves as a source of rotational forcing frequency and as a modulating frequency for the gear mesh associated with that stage. Because multiple GMFs may fall within similar frequency ranges, spectral interpretation requires careful labeling and validation. Two-stage gearboxes are common in industrial applications where large speed reductions are required, making accurate forcing frequency calculation essential for reliable condition monitoring. In a two-stage gearbox, each gear pair generates its own gear mesh frequency. GMF for the first stage is calculated using the input shaft frequency and the number of teeth on the first stage gear. The second stage GMF is calculated using the intermediate shaft frequency and the tooth count of the second stage gear. These GMFs are independent but coexist in the vibration spectrum. In some cases, harmonics of the first stage GMF may overlap with the second stage GMF, increasing analysis complexity. Accurate calculation and clear documentation of each GMF are therefore essential. Engineers often use spectral overlays and frequency markers to distinguish between stage-specific components. This systematic approach ensures that faults are correctly attributed to the appropriate gear stage, reducing the risk of misdiagnosis. Sideband behavior in two-stage gearboxes is more complex because multiple shaft speeds can act as modulating frequencies. Each GMF may exhibit sidebands spaced at the rotational frequency of its associated shaft, as well as at frequencies from other interacting shafts. For example, the second stage GMF may be modulated by both the intermediate shaft speed and the output shaft speed. This results in multiple sets of sidebands, which can overlap and create dense spectral patterns. Careful calculation of all shaft frequencies is required to correctly interpret these patterns. Despite this complexity, sidebands remain one of the most powerful indicators of gear health. When analyzed systematically, they allow engineers to pinpoint fault location and progression even in multi-stage gearbox systems. The image represents an industrial gearbox application where vibration-based diagnostics are applied for condition monitoring and fault detection. Computed forcing frequencies are fundamental tools in engineering diagnostics and condition-based maintenance. By comparing measured vibration spectra with calculated shaft, gear mesh, and sideband frequencies, engineers can quickly identify abnormal behavior and assess gearbox condition. In practical applications, these calculations support fault detection, severity assessment, and maintenance planning. Trending GMF amplitude over time can reveal progressive tooth damage, while increasing sideband energy may indicate worsening modulation due to defects. When combined with time waveform analysis and operational data, forcing frequency analysis provides a robust, defensible basis for maintenance decisions. Ultimately, the professional application of forcing frequency calculations improves gearbox reliability, reduces unplanned downtime, and supports safe and efficient operation of rotating machinery across a wide range of industries.